Hello, class. This will be the recorded lecture for section 7.3, which deals with the main theorem in statistics called the central limit theorem. So the first recorded lecture will be trying to introduce the concept, and then the next couple lectures we'll talk about how to do some calculations. So the idea here of the concept is such that the theory behind the central limit theorem is that if you do enough samples or you do enough experiments, every distribution's mean or average will eventually approximate a normal distribution. You can see where the normal distributions become so important now. And so again, we're just talking about the mean. There's some other things as well, but we're first introducing the mean. And so the idea is I'd like to just show you an example of how this thing gets calculated. And so if you remember the idea of generating a probability distribution function given an experiment, and we talked about that in chapter 6, where given this experiment, you'd be able to calculate the probabilities of each event occurring. And so what I like to do if we were together in a classroom is to show you how to do this with the idea of rolling 2 dice. And so the experiment that I am going to offer is this idea of rolling 2 dice and adding them up, or the sum of rolling 2 dice. And so if you're familiar with 2 dice, it has the numbers between 1 and 6 on it. And we're going to add them up. So the minimum number you can get is the number 2, which are 2 ones. And the maximum number you can get are 2 sixes. And you can see there's numbers between 2 and 12 respectively. And what I have here is the sample space. And so these are all the possible outcomes. And you can see that if you count all these up, there'd be 36. And here would be the probability. And what I mean by the probability is that, for example, 2, there's only one possibility. So 1 divided by 36. The one that occurs most often is the number 7. And you can see that occurs 6 out of 36 times. So just to refresh everybody's memory, here is the theoretical probability distribution table or function for this specific experiment. So I've done this, but just to walk you through this, here's our X values. So that's the sum between 2 and 12. And then here are the probabilities now in, make that a little bit bigger for you, now in decimal instead of fraction. And so you could see this would be 1 divided by 36, 2 divided by 36, and so on and so forth. So remember that when you add these all up, it better equal 1, and there it is, or we did something wrong, right? And so how do we calculate the mean again? Well, remember the mean is the number times its probability, which is this column here. And then what we want to do is add these all up. And I did this here so I could label it a little bit better. And so you could see the mean when we add that whole column up is the number 7. Like, oh, and you know, if you think about it, it's right in the middle here, and it's the one that occurs most often. So it kind of makes sense. And so the other idea is, what is the standard deviation? Well, here, basically, you take the X minus the mean, and then you square it, and then you multiply times the probability. So I did this in this column. And then when you add this whole column up, you get the variance. And so the variance is the square root of the standard deviation. So down here, I took the square root of 5.8333, and you can see you get the number a little bit over 2.4. So, and that kind of makes sense, right? Because you can see there's quite a bit of numbers here. A lot of the probabilities that are high are close to the mean, right? 6 and 8 are the next highest, but we do have some extremes all the way down to 2 and all the way up to 12. So that if you think about it, that standard deviation should feel right as well. And so going back to, I plopped this right into our PowerPoint presentation that I did right there in the spreadsheet. So what does this mean? Well, what the central limit states is this idea that if you do larger and larger samples, so if we rolled it 100 times, 1,000 times, 1,000,000 times, the mean of this distribution is going to approximate a normal distribution. And if we were together, I would pull out my bag of 100 dice and hand them out, and we would show you an experiment to show you how this works. And so I do have some old classes that I will show you what we did. And so the idea is that it approximates a normal distribution. And what's interesting about it is here is a couple experiments that we did. And so the first one here is experiments of, here is the values of adding 2 all the way to the number 12. And so what I did in a class, I think it was last year, not last semester, is there was 30 some students in the class, and we spent about 15 minutes gathering the data, and the total number of rolls was 4,179. And so when you do those, it's quite a bit, right? And so we would hope it would approximate the normal distribution using the central limit there. Well, I showed you that the mean theoretically was the number 7. And so I did the calculation. And so these are some rolls of different tables. And then here's the total. So this is the total number of rolls for each one. And this is our X value. And remember now we're talking about frequency. And so what I did here was calculate the total number of rolls, which was 479. And then here I can put total here as well. And then I wanted to calculate the mean. So basically I multiplied 2 times 130 and got 260, et cetera, all the way down this column. So this would be X times the frequency. And you know, a better number here would be frequency. And so X times the frequency, and then you add these all up. And so the total would be 29,204. And so how do you find the mean? Well, it's the total, adding all the dice up, divided by the total number of rolls. And you could see that the value is 6.9888, super close to 7, right? And so this is not a proof, but this is just a demonstration on, hey, this thing actually works. And look what the graph looks like. So I graphed the X values on the horizontal axis and the frequency or the Y values up here on the vertical axis, which is the frequency. And you could see it looks just like a bell curve. And you could see the mean, the median, and the mode occurs right in the middle here with regards to that. And so it looks very bell curve-like with regards to the calculation. And so I actually did another one, and this was a class where we did 1,425. and it didn't get as good. You could see that this thing is a little chunky with regards to that. And you could see that our mean ended up being 7.27, which is a lot farther away from 7 than 6.98, right, up here. And so with regards to this demonstration and experiment, it doesn't prove anything, but it does demonstrate that the central limit theorem actually works. And so here's a couple key attributes to it. Number one is that when we do these calculations, that the mean is the mean. And again, that's kind of nice. And so the mean of the distribution would be the same as the mean of the population. So the mean of our distribution population was 7, we calculated it. So the mean equals the mean of our experiment as well. But this idea of standard deviation changes, and sometimes it's called standard error as well. And it's basically the standard deviation of the population divided by the number of samples and the square root of that. And so this standard error, or the standard deviation for the central limit theorem, as I like to call it, is the standard deviation divided by n. So for example, and I just did this to make the numbers easier, if you had the standard deviation that we calculated from the population of 2.4152, and you had 100 rules, what would be the standard deviation using the central limit theorem, or what we call standard error? You would divide that by the square root of 100. And I did that because that's nice. That would be 10. And so when you move that, you could see that the standard deviation gets a lot smaller really quickly. So here's another example. If we have a certain college, the mean number of hours of television watched is 10.5 and a standard deviation of 3.6. So if we randomly pick 16 students, find the standard error or the standard deviation for central limit and its mean. Well, the mean's the mean, so that one's really nice. And so 10.5 is 10.5. And so this one's strategically set up where you have the square root of 16, and the square root of 16 is 4. And so 3.6 divided by 4 is 0.9. So we're going to use these types of calculations to make predictions on experiments using sample means and the central limit theorem a little bit later. But let me just show you a couple important attributes. This is the theorem. It says let X be the mean, and the idea is that it will work with any distribution. And if you don't know what the distribution is, the theory behind it is that your sample has to be greater than 30 to use the central limit theorem, where the mean will be the mean, and the standard deviation is the population standard deviation divided by square root of n. If you do know that your experiment or population is a normal distribution, then the sample size doesn't have to be greater than 30. It could be smaller. And so as we kind of show you this idea, is that if a sample size is 3, it could look like this. If a sample size is 10, it could look like this. And a second one there, and you can see that those are skewed. If we start getting a sample size that's pretty big, it starts looking like a normal distribution. So let's take a look at a couple of these. So can you use the central limit theorem in this application? Sample size of 45. Boom, the answer is yes right away because it's greater than 30. And so here we have the mean and the standard deviation. So you'd be able to find the mean as 15 and the standard deviation would be 3.5 divided by the square root of 45. Here, we have a sample size of 8, but it's from a normal population, which means it already is a normal distribution. So then you can use the central limit theorem. So those are the two criteria. As long as n is greater than 30, you don't have to care about the distribution. But if it's less than 30, you want to see this idea of normal. And then the last example here is we have a size of 24 and you don't know what the population distribution is. So the answer would be no, because it has to be greater than 30. So, well, that ends this first introduction of the central limit theorem. And the next lecture, we'll talk more about actual calculations using the central limit theorem.